Hey, I'm Bob Wormsley, and in this constraints video we'll look at the forces. We'll see how we can apply both attractive and repulsive forces to particles. We'll use these forces in conjunction with connections. And we'll look at how we can map the strength of constraints using various particle parameters, like radius. So let's get started. So here we have an emitter set to a defined emission. We've got it as a 3D grid with 10 particles on the X and the Z axis and only one on the Y, and all the speed has been taken off. So if we spawn the particles, that's what we get. So let's just give this defined emission a box size of 0, and it'll just get rid of that bounding box. Right, so our particles have got a radius of 6 with a variation of 4, which means we've got a variation of radii for the particles. And this means, by the way, this 4 centimeters variation, it's 4 centimeters either side of the radius amount you define here. So these particles are anywhere from 6 minus 4, which is 2, to 6 plus 4, which is 10. So these particles are anywhere from 2 centimeters to 10 centimeters in radius. That's how that variation amount works. And then in the display tab, what we've got is we've got them set to circles filled, and we've got the colour mode, just a gradient random with this colourful gradient. It's a temperature gradient, I think, which means that we get all of these nice random colours. So there we've got static particles in this grid. So let's have a look at the collision type that we haven't done yet, which is forces. So we'll go to the dynamics, constraints, and we're going to go to the forces tab. So the forces is slightly different to connections that we've looked at already, and that's because the particles don't actually get connected with a spring. They are given a force. So let's just make this active. So how the forces works is this. Each particle is given an attraction and a repulsion force. So it's going to try to suck particles towards it, and then push them away with the repulsion. If I hit play here, absolutely nothing is happening. Why not? Well, it's because, similarly to some of our connection modes, we have this search radius. So what it's saying is each particle is going to look within a 20 centimeter radius to see if there are any other particles. If there are, it's going to apply an attraction force. But because these particles must be further away than 20 centimeters, so let's just do our old trick. We'll get a sphere, and let's make the sphere 20 centimeters, and we will move that to on top of one of the particles, because then we clearly see that the search radius of this particle is not getting any other particles. So let's just increase the radius of that sphere. So it needs to be about 50, 52, something like that. So let's just get rid of that sphere. So in our constraints, let's up our search radius for our attraction force to, let's just say, 52. Now let's see what happens. Hit play. Okay. So those particles are being kind of pulled towards each other. But we also have a repulsion setting, which you can see is set to 1%. And the attraction force is set to 1%. So this is going to give some kind of equilibrium to this simulation. If they're within this search radius, it's going to pull the particles towards them. But then once it gets into the repulsion radius of 10 centimeters, it's going to try and push them away. So you're going to get this kind of push-pull of the particles. And what it'll do this with up to however many particles are put in this forces limit. So we've got 16. So at the moment, each particle will have an attraction and a repulsion force for up to 16 other particles. And the result is we get this kind of effect where they're all kind of pushing and pulling and moving around each other, which in itself looks quite nice. But you can see we've actually got them intersecting, which isn't really what we want. Now, we could try and stop them from overlapping each other. We could try increasing that repulsion force. I'll put it up to 3%. Let's see. That's perhaps helping. I mean, this is working in 3 dimensions, remember. So, but no, they're overlapping each other still. So let's put that repulsion force up even more. And I'll just increase that radius slightly. So now they're kind of less likely to intersect because the repulsion force, once they get into 13 centimetres, is pushing them apart. But then they're getting sucked back in by the attraction. So it's a constant give and take. So instead of trying to stop them from intersecting, from upping this repulsion, let's just put that back down to 1. What we can do is we can activate the particle collisions within constraints. Let's just activate that, hit play. And now we're getting a really nice look because these particles are colliding off each other and they're not intersecting. And we're getting them clumping up into various different groups. And this is because some of them are getting away from this 52 centimetre attraction. If I up that to 100, or even let's put it up to say 300, and then increase this forces limit, now they're all getting sucked back in again. And now they're all, oh, that's really, that's taken in every single particle. Now you've seen that even though we've just increased the radius, we haven't increased the attraction strength there, but they're going a bit mad. Why is that? Well, that's because it kind of multiplies this attraction force, the more particles that are involved with it. So if you think that this particle here is trying to pull in 50 others, but so is this one and this one. So they're all pulling them into each other. So the more particles you have and the more you have in this forces limit, the more strong this force is going to be, even if you're not increasing this attraction strength here. So let's just reduce that back down to 16 where it was. Okay. So another thing that we're able to do, which is quite fun, is we can obviously use these forces constraints along with the connections that we've already looked at. So let's just go to my emitter, make sure that we're viewing constraints, display constraints. Okay, good. And we'll go to connections. Let's put some distance connections here. So we're going to connect within distance and let's connect. I'm just going to guess at, say, 20. So let's see what happens now. Okay, so that's quite interesting. So as they get closer to each other, they're making connections and they're joining up. And it's obviously changing the way in which that sim looks. So let's just go back to my forces. I'm going to put this back down to that 52 radius. And we'll put this back down to the default, which was 10. Okay, here we go. All right. And because we have got this only working in a 50 centimetre radius, we're getting quite a regular grid here. It's creating quite a regular pattern. Now, I can imagine this would be very useful. I can imagine this as being some kind of molecular render of some revolting virus in a Petri dish or something like that. But you can see that this has got a really nice kind of scientific look to it, and that is a look that you're getting very, very cheaply. So that's using these connections, which is looking good. Let's just switch off those connections for now and explore some of the other forces settings. So another thing that we're able to do here is we're able to map the strength of, let's just pull that up. We're able to map the strength of both the attraction and the repulsion forces to a particle parameter. So let's have a look at what that might look like. I'm going to go to the attraction and I'm going to map. I'm going to put this radius up to, say, 300. So it's going to attract everything and they're all going to come in really quickly. But what I'm going to do, I'm going to map this attraction to the radius of the particle. Now remember, our particles are anywhere from 2 centimetres radius to 10 centimetres radius. So in the min we'll put 2 and the max we'll put 10. And I'm just going to change this graph to something like this. So what this is saying is, if a particle has a radius of 2, it has 0 attractive force. If it has a radius of 10, it has the full attraction force, which is defined by this, which is 1%. So what we should, in fact, let's just make it more obvious. So I'm going to do it something like that. So what we should see here is, let's have a look. Only the larger particles have an attractive force. And that's clearly working, isn't it? All right, so that's interesting. And we can make that more subtle by giving it more of a curve. So we've got some nice control there. Conversely, let's just put that back to none. So it's back to where we started. Put this, we'll leave maybe leave the attraction at 200. So this is what we've got by default. All right. So now let's map this repulsion. So we're going to map the repulsion to the particle radius. And this time we're going to put from 2 to 10, because that's our possible particle radii. And let's say full repulsion for small particles, no repulsion for bigger particles. And we might have to turn this repulsion amount up, but let's just have a look and see what we've got. And I'm just going to increase that repulsion radius. And let's increase the repulsion. There we go. So what we have got now is the smaller particles are being repulsed, but the larger particles aren't. And we're managing to keep the smaller particles towards the outside of our mass of particles. And that's looking interesting as well. Let's just really crush that down. So it's only the very, very small ones which are now kind of floating and keeping around the outside of our particle blob. So that's looking interesting as well. So with particle forces, what you have basically got, you are pushing and pulling the particles with both the attraction force and the repulsion force. And if you want to then map them, you can to get different looks. You can also combine this with connections and all of the other constraints to get particles to behave in very unusual and organic ways.